Let's look at the second example, also from LeetCode, count of smaller numbers after self. So here's the problem description. We are given an integer array, and we're supposed to find out for each element in the array how many numbers that are to the right of the element and are smaller. So we output this array that gives that information. So for example, if the input is 5261, the output should be 2110 because to the right of 5, there are two numbers that are smaller, 2 and 1. To the right of 2, the one number that's smaller is 1. To the right of 6, there's one number smaller, that's 1. And to the right of 1, there's no number, and there's no number smaller, so it's 0. So that's the problem. So naive approach is for each element we scan the rest of the array and to find out how many are smaller than it. This will take quadratic time. And this is also related to the problem of counting number of inversions, which you may or may not have encountered. An inversion is a pair of element in an array such that the index is I less than j, but ai is greater than aj. So one way to solve this counting inversion problem is to use divide and conquer. Essentially, you'll be doing a merge sort. And then while you're merging, based on the position, you will know how many things that, suppose you are merging the first half with the second half, and every time you see an element in the, I guess in the first half, you know where this will go in the second half, then you know how many elements that are in the second half that are actually smaller than this. So if you just need a total count, that is simply one line change, one additional line in merge sort code to do this. But for this particular problem, I think you need a little bit more code. You need to keep track of information for each element, what is indexed, and then adding the number of elements to the corresponding position. So I think it shouldn't be too hard. Yeah, I guess just that probably will be sorting a pair where the first element is value, the second is its original position, and then we can use that to update the answer array, the answer vector. But another solution is to use a segment tree for this problem. So if you are not familiar with this approach, this may sound a little bit strange because why do we use segment tree? There's no update here. We're just counting things. There's segment tree support. The main reason we want to use segment tree is to support a point update, but there isn't a dynamic update here. So why? So I view this as a second major application of segment tree. So which is so I coined the term this 2D quadrant problem. Let's change the. So 2D quadrant problem is we are given a bunch of points in 2 dimensions, and what we want to know is for each point we want to find out information about point in one of the 4 quadrants relative to that point. So let's look at why this problem is a 2D quadrant problem. So we are given a bunch of values in an array. So then each of the elements have 2 properties, the location in the array and the value. So I use this to graphically illustrate this point. So this is represent 5. So from here goes up is 5, and the position is the first element in the array, and this represents 2, this represents 6, and represents 1. So the query we want for this is for the 5, we want to know how many points are in the, I guess this is a 4th quadrant, if you will, this as the origin point, to the right of this point and to the lower of this point. So how many points are there? So it turns out there are 2. So So this is every query is about the quadrant relative to a point, and the point have two properties, and these two properties, of course, they are sorted. That's why we have this concept of quadrant. So when we have this kind of 2D quadrant problems, we can turn that into a range query with dynamic updates, and then we can solve it with the segment tree. And the trick is we will build segment tree on one of the properties, and then we will sort on the other property. And then we will process the elements by the sorted order, gradually add them into the segment tree. So for example, for this problem, one way is we build the segment tree based on the array size. So and the element is simply going to be counting. So the element in the array in the segment tree is going to be either 1 or 0. So initially it's all 0. And then we will sort these points, this 5, 2, 6, 1, and then we will add them one by one. So we will first add the point 1 to its correct positions, the last one. So we'll add a 1 here. And then when we add 2, we will be querying. So we know the 2's position is also the second element in the array. So we know we'll be looking for everything to the right of this 2, and we want to sum up the thing in the segment tree array. So which is just 1. Because we are, by summing up this 1 or 0, we are summing up how many elements have already been added. And because we are adding the element by order, when we sum up, by the time we sum up the value for corresponding for this 2, only the value that is smaller than 2 has been added. And we are querying to the right of this point, doing a range query. So therefore, we are getting the correct value. So after we query this to 2, we will add 1 here. So after we process 2, we will the array in this base array for SegTree will have 0, 1, 0, 1, signaling that we have already added the element for the second and the fourth element. And then when we query 5, we will be querying everything to the right of the first element and see how many are there. We're basically summing up this 1, 0, 1, we get 2. So the answer for this is 2. So that's one way to do it, is to build the segment tree on the array position, which is usually the more natural one to do it. But for this problem, because the specification is actually the elements are not very large. So let's go to the LeetCode. So the constraint is that the size of the array up to 10 to the 5, and the value of the array only up to from negative 10 to the 4 to positive 10 to the 4. So actually, we can also build a segment tree on the y-axis, so on the values. So then we will be processing the element one by one based on their array. So this is what my code does. Because for the other one, I have to create the pairs and then sort them, sort this element, because I need to remember where their position. So using this method, I don't need to do that. So I think for this particular problem, this is slightly better. But this is a more constrained. This approach works only when the this approach is convenient only when the value are small. If they are large, then if I still want to use this, then I have to do coordinate compression. I have to take all the values, sort them. Then I know for each value we can map to a index, and the total number index is bounded. So one thing that we need to make sure when we use segment trees is the base array cannot be too large. If it's too large, then we will not have enough memory for it. Okay, so here's my code. I guess this slide, there's not much information in it because that's basically just a SegTree implementation. So this is the more interesting part. So given this array, then I will first create an answer array to store the answer, and then I will create a segment tree based on all possible values, because the constraint guarantees that the smallest value is negative 10 to the 4, biggest is positive 10 to the 4. So the number of possible values is 20,001. And then I create the SegTree using this, and then I will process all the element in here. So this and I will process it from the end forward. So I will first process this last element, and then I will just add it to its corresponding position in my segment tree. So I guess the index would be actually be 10,001 because the 0 position in the segment tree base array correspond with the value negative 10,000. So I will add 1 there. And for the next element, then I know all the values that have been added to the segment tree are the ones to my right. So the only thing I care about is how many value are less than 6. So I can do that using a range query. So there are 2 steps. The first thing is I will update the element corresponding to the value. So I need to add 10,000 to turn negative 10,000 to 0. To be a valid array index for me, and I will update that to 1. So set that value. Well, here the update is actually increment. So this is So this is one change from the template code earlier. This is plus equal because there may be multiple value. The same value may occur multiple times. So I'm really counting how many times those occur. So this need to be this update is actually add 1, and then I'll just query from 0 to here. So basically, how many elements are less than me? So that's the meaning of this query. How many elements in the segment tree are actually smaller than me? And because I'm processing from right to left, so I'm basically querying how many elements are to my right and less than me, which is what this problem asks. So then that's it. This will solve this problem. So in this case, we can see that we are using a second application of segment tree, which is this 2D quadrant problem. So to recap, the problem have the property that we are given data points. They have 2 properties, and both can be ordered. And the problem requires us to query information for every point we want to know information about the one of the 4 quadrants. So in this particular example, we are counting the number of points. Sometimes we may be wanting some, sometimes we may be wanting other, or max, or I think max should work. Yes. So essentially, things that can be computed using associative functions. Because if you have this quadrant direction, then what we can do is we can build the SegTree on 1 dimension and then sort based on the 2nd dimension, and then just process element based on that. So the processing updating order ensures 1 dimension, and the query ensure the other dimension. So we can do this quadrant style queries.